So very good afternoon to everyone. So we will be so today it is like a week 4 tutorial of the principle of the casting technology, and I am Rohit Gehlot. I will be taking this. So can anyone confirm that if I am audible or not? Uh, yes, brother Arjun. You want to say something? Okay. Okay. So we will wait for like 4 minutes more. So see if anyone else joins. Then we will start. Good evening. Good evening, Doctor Govind. Okay, so let's start week 4's tutorial. So like in the last week we studied about the we like studied different problems on the for the top gating system. So today we will be covering majorly the bottom gating pouring problems and also the gating ratio problem and finally we will be concluding with the air aspiration problem. So today firstly we will be so first I will this is the problem number one. So there is a one figure is given and the cross section area of the gate is 10 centimeter square, and then we need to calculate the filling time for the gating system. So firstly whenever the problem comes, whenever I think someone wants to join. So firstly, like whenever you encounter any pouring filling problems, you need to see like whether it is a top gate, bottom gate or a parting line gate. So from the figure, like it can be seen as the mold is above the parting line, so it is a bottom gate problem. As you can see, the mold will be filled from this position, like with the hole you can see. So this is a problem of the bottom gating system. So like the derivation of the bottom gating system has already been covered in by the Professor Jha. So but still I will it will be helpful for a recall. Like I also covered this in the previous tutorial also. For the top gating and the bottom gating system. As you can see, it is a simple derivation from the Bernoulli equation itself, and then the final formula uh, which you get for the for the bottom gating. I will write it for you. Then you can try to solve it. So this is the filling time for the bottom gating system. Uh, it is equal to the area of the mold divided by the area of the gating. So the derivation has already been present in the theory parts of the week force tutorial. You can go through that if you have any doubt like how it is derived, or you can watch the week 3 tutorial class for derivation. I request each one of you to please try to solve this. So the major issue is whenever okay, so whenever
Hello, sir.
yeah, hello.
Yes, sir. Previously, it was area of casting divided by area of gate into 1 by root 2g.
Okay,
Now you are saying it is root 2 by g.
so previously we did only for the top gating system.
No. This bottom getting also you are given the formula, and also we are solved some also for bottom getting.
Okay,
That is AC divided by AG into 1 by root 2g.
okay, okay. So
Uh,
okay. So the thing is
into
it.
into into
Okay,
2 times of root h is c minus root of h c minus hf.
okay. So area. So I used different terminology. Like area of the mold is equal to the right area
Area,
of the C, right? So it is
yeah.
area of the cast or area of the mold which need to be filled itself. So both the terminology is the same. Use different terminology, but the inference is the same for
No.
both the
That is okay, sir. What I am asking is A C or A M. It is not problem.
okay, okay.
AC divided by AG into 1 by root 2G. The formula
Okay.
is 1 divided by root of 2G.
Okay, okay. So, okay, so I might have forgot. So for when you derive the formula, there is like 1 by root 2g, and it is again multiplied by 2 times.
Okay.
So it comes to root 2 by g. This is the correct formula.
Okay.
Okay.
Which is
So yeah.
both are same.
So the root two and root two, if it get cancelled, then you will get root 2, or na, root 2 at the
Yes.
bottom, at the top side,
Yes.
na. So
Yeah.
it is the same, yeah. So
Okay.
okay, so you need to like use this or this, whichever form you want to use. Like as root 2 and 2 will get cancelled out, and you will get root 2 at the top, na.
Okay. Okay.
Okay, yeah,
Yeah.
okay, yeah. So here HT is the total height, which is the height of the sprue and height of the pouring basin, and while HM is the height of the mold cavity. So like the majorly the students like did mistake in like inferring like which term is which from the diagram. So like here HT is, I write it. I think someone wants to learn. No. So here HT is the like total height. And HM is the height of mold cavity. So anyone who like uh, so anyone who get the final answer, like we can like try this. Like from the figure, you just need to put the values in in the formula, and then like find like the what will be the filling time for this bottom heating system. So from this figure, like if you see this area of the mold or the cast, it can be like directly calculated from this. Like this need to be filled. So the area will be like simply 1 multiplying by 0.5. So this will come as like 0.5 meters square. Then area of the gate, here it is given as like 10 centimeters square. So you need to take like the you need to carefully convert to meter square. So it will be like it come as like 10 to the power minus 3 meter square. Okay. So and after that, like HT, which is the total height, from here you can see like the HT is this one, which is 0.3 meter, and HM, is this 0.25 height of the mold cavity. So please try to put these values in this formula and then tell what will be the filling time for this bottom getting system. So when you will calculate, area of the mold is 0.5 meters square divided by area of the gate is 10 to the power minus 3 into 2 divided by 9.81, as the unit is consecutive. We are writing it in meter per second and multiplying by root 0.3. 0.3 minus 0.25. Anyone who solved this? And this will come in seconds. So when you will solve, it will come as around 73.17 seconds. Anyone who got this answer, or anyone who has any doubts in this, if it is clear, we can move to the next problem. Okay, then let's move to the problem number 2. So in this, the question is 180 centimeter long down screw. So this is a 180 centimeter long down screw has a velocity of 2 meter per second. 2 meter per second at a section where the pouring basin meets the down screw. Okay, a constant. This is the pouring basin, and it meets down screw at here. Okay. So a constant head of molten metal is maintained by the pouring basin. Okay, so here it maintains a constant head, and then the end of the down screw is connected with the runner figure as shown, which fills the elliptical mold of dimension 30 centimeter and 10 centimeter and a height of 60 centimeter. If the area of the gate is 15 centimeter square, then find the mold cavity time, mold filling time. So this is the similar problem as before, but the difference is there are 2 to 3 things different. First, the elliptical mold cavity needs to be filled, whose dimensions are this and this, and the height of this. Okay, and then you need to calculate the HC here. It is not given here. The velocity is given. So firstly, you will need to calculate the HC, and then you can use the bottom getting filling system, as it is also you need to fill above the parting line. This is a bottom getting system. So please try this.
आपने जिस व्यक्ति को कॉल किया है वो अभी दूसरे कॉल पर व्यस्त है। कृपया आपने जिस व्यक्ति को कॉल
हेलो, हाँ सर, हाँ सर, हाँ कभी भी चलें सर। आज मतलब मैं तो 6 बजे बाद फ्री हो जाऊंगा। आप बताना, आप कहाँ हो? अभी लैब में हो? अभी तो 4 से टीए ले पड़ता है ना सर। अभी वही ले रहा था। हाँ बिल्कुल बिल्कुल, उसको बोल दिया ना सर्विस को, मैं फोन करूँ वो बुरा बुरा मोरा मान जाए कि मैंने फोन नहीं किया है। अभी अभी, हाँ अभी फोन कर देता हूँ उसको। ठीक है ठीक है ठीक है ठीक ठीक ओके ओके। Okay then, so we will solve this problem. So as you can see, firstly, like whenever you see uh, any kind of like gate filling, mold filling problems, you need to confirm whether it is top gate, bottom gate, and parting gate. So it is a bottom gating system. This is confirmed. Now we need to see again we will write the formula. You can derive it also, but it is good like if it is a simple problem, then you can directly use the formula. So like T bottom gate filling is again area of the mold divided by area of the gating system, multiplying by 2 by root G, then root of HT minus root of HT minus HM. So here this let height of the, so like let assume that this height of the molten metal column is or the pouring basin is, this is like HC. So this we need to calculate, and here the velocity at point 2 is given as 2 meter per second, right? So we when we will apply the Bernoulli between 1 and 2. So like if we apply Bernoulli equation between point this 1 and then point 2, so P1 by rho G, so I will write, so we will get like directly V2 velocity at point 2, you'll get velocity at point 2 as root 2g and then hc. The velocity is given to us like it is 2 meter per second, so let's convert it to into centimeter per second. So it will be like 200 centimeter per second and equated to 2 multiplying by g, and it, in the constant is given to take it as like 10 meter per second, so I'm taking it in centimeter per second square. So it will be 1000 centimeter per second square times hc with as which we need to calculate. From here like we will get this hc as 20 centimeter. So this height we one second. So we got like this height as 20 centimeter. And this height we already know like 180 centimeter. So we got the total height HT as like 180 plus 20. It will be 200, and HM we already know like 60. So please try to solve this problem now, and like tell me like what is the filling time for the gating system. कहाँ है भाई, क्या कह रहा है? कितना काम करेगा भाई, दिखता ही नहीं आजकल रूम पे, ज्यादा काम हो रहा है क्या तेरा? साला दिख नहीं रहा, आ गया है, फिर भी ना हाल चाल पूछ रहा है ना कुछ, कोई तरीका है क्या भाई तेरा? मा, माफ माफी वाफी कुछ नहीं मिलेगी भाई, मारपीट होगी अब तो। आज 8 बजे मिलते हैं, फिर चलते हैं 8 बजे कहीं खाने पीने। टाइम है ना भाई आपके पास? ये बड़े बिजी आदमी हो, क्या पता है भाई। अरे ये सब बड़ी बड़ी बातें हैं, ठीक है 8 बजे चलते हैं ना। ठीक है ठीक। So anyone who got the answer? So one more thing you need to like take care here, as the elliptical mold is given, so we need to calculate the area of this elliptical mold, and then the area of the mold is given as, for the elliptical it is given as pi times A into B. So like if this is the like elliptical mold, then this is its A and this one is its B. Okay, so these dimensions are given like 30 and 10 centimeter, and then its height has already been given. Okay, so let me clear this thing. So when you will like calculate it, then T filling will be like area of the mold will be pi times A into B. A and B are given as 30 and 10. So we will get it as like 300 pi centimeter square, and then T filling will be 300 pi. Area of the gating is given to us as 15 centimeter square. G times root 2 by G is like in centimeter, we need to centimeter per second square, we need to, right? This, and then root total height is 180 plus 20 centimeter, so this will be 200 minus root 200 minus 60. So please like try to solve this. If you won't solve, if you won't practice, then at the end of the exam or in the exam you might face problem. So this, if after calculation, you will get a 6.49 seconds. So if anyone has any doubt, like please let's discuss this now, or I will move to the next problem. Okay, then if no one has any doubt, then let's move to the problem number 3. Okay. Okay. So the problem number 3 is a combined problem of the top gating system and the bottom gating system. So if you see a cuboidal casting of 30,000 centimeter cube. Okay, so 30,000 centimeter cube. This is the total volume. Total 30,000 centimeter cube total volume has to be filled with a parting gating system, as shown in the figure. This is the figure. The height of the mold cavity above and below the runner is equal. So this is also 300 mm. Then the total height, the total liquid head is maintained constant such that it is equal to the mold height above the runner plate. If the runner has a uniform cross section of 20 mm diameter, then this has the diameter of 20 mm. So from here you can find the area of the gate and the total time to fill the cavity. So this is the parting line. This is the top gating system. This will behave as top gating system, while this will work as the bottom gating system. So let's assume that this is time to fill this is T1 and time to fill this is T2. Okay, so the total filling time will be for this type of system will be like T1 plus T2. Okay, like the T1 is the top gating system and T2 is the bottom gating system. So this we need to calculate. Okay, so for the top gating system we have already like calculated. Like firstly, as the volume is 30,000 centimeter cube, this will be like 15,000, and above one will also be the 15,000. So for the top gating system, the T1 will be the 15,000 centimeter cube. divided by area will be, I converted it the centimeter cube to mm cube, divided by area of the this gating system, like which is like pi by 4 times d square, which is 20, times velocity. Here velocity will be root 2 times g is 9810, then height which we need to fill is 300 mm, this one. Okay, so here like t1, if you will calculate, you will get as 19.68 seconds. So this is for this filling of this top heating system. So can anyone like calculate for this bottom heating system? This is the same as like previous two problems. I think you should be like able to solve this now. So there are like two things you can do. Like firstly, by direct observation, if you will see, like here like T filling for the bottom gating will be just twice of this T1. And how I like told this, if you will see here this height, this is the total height ht, and this height is which we need to fill hm, these are equal. Okay, so if you will write the formula like for T filling for the bottom gating system, which is equal to the area of the mold divided by the area of the gate times root 2 ig, then here if you will write this ht minus root ht minus hm, right? This ht and hm are equal, so this term will get equated to 0. Okay, now if you will see like this top gating system, the formula is like volume of the mold divided by the area of the gate times velocity, which we write as root 2 g hm, right? So here like if you will multiply it like if you will see, it will be like root 2g. If you multiplying by root g, then root 2g ht, and then multiplying by this am, it will become volume of the mold. Here eg is the same, and then here root 2g hm will come. Okay, as hm and ht are the same here, so this will be like twice of this top gating system filling. So we can directly like do twice it, or we use this formula also, we'll get the same thing. So T filling for the bottom gating system, so T2 will be like 2 times 19.68. If you will see, it will be like around 39.36 seconds. Okay, so let me make some space here. So the total filling time, which is sum of the T1 plus T2, it will be 19.68 plus 39.36. If you will calculate it, it will be like around 59 seconds. This will be the final answer. So anyone who has got any doubt or so anyone who has got any doubt in this problem, like we can discuss it now. Okay then. So it's not a so from this is the like this was the last problem for the filling of the bottom gating and the top gating systems. So the problems may get complicated and if the like how the problem may get complicated, like the shape of this gate which needs to be filled may get complicated, like trapezoidal or some conical, which in the problem in the exam may be given. So you may need to like calculate via the integration method and all, or there might be some this above bottom gating system, there some riser provision of riser may be given, or some hollow kind of cavity you need to fill. So these are the ways the problem may get complicated. So you need to see or need to solve more problems to clear your doubts and or basics. Okay, then we will move to the problem number 4. So this is a simple problem. Like this we have already like covered in the previous numerical itself. It says like in a sand casting operation, the total liquid head is maintained constant such that it is equal to the mold height. Like, just what we did in the previous question. That's for a recapitulation. Like it is maintained constant such that so here it is given like ht is hm. The time taken to fill the mold with the top gate is for top gate it is ta. This is for the top gate system. If the same mold is filled with the bottom gate, the time taken is tb is for the bottom gate system. Okay. Ignore the time required to fill the runner and the frictional effects. Assume atmospheric pressure at the top of the molten metal surface is the relationship between the TA and TB. So like this we have already solved, like it will be twice TA and TB. TB will be twice the TA, but still we can again see like for the top getting the bottom getting system, it will be area of the mold divided by the area of the gating system times root 2 by g, then multiplying by root ht minus root ht minus hm. Okay, so this will be equal to 0. Then again you can find out for the top gating system, this will be the volume of the mold divided by the area of the gate, and velocity if you write it in 2g as time. So now again you can equate it, and then which you have already solved it in the previous problem, you can get it. Okay, so now we will come to problem number 5. In a gating system design, a down sprue of 180 mm in length has a diameter of 20 mm at its top end. The liquid metal in the pouring cup is maintained up to 60 mm in height. The diameter of the down sprue at its lower end to avoid air aspiration effect will be. So can anyone tell me what is the air aspiration? As in the theory part, Professor Jha has already covered this. Anyone who has watched and who would like to convey his or her thoughts? Okay then. Okay then, so if you will see like about the air aspiration effect. So what happens like in the air aspiration effect, like so this is generally a provision. So if it is like and what happens like if it comes like, then the entering of the gases from the gases will be again re-entering in your system from the molten melt stream, if they like if it is not taken care of. So like if we, for example, if you see here, so if you are, suppose if you are using a straight sprue, okay, here the pressure is atmospheric pressure, okay, and this height is hc, say this height is hc, and here this is 1, here this is 2, and this is suppose your mold or cavity which it needs to be filled, okay. Here also the pressure will be atmospheric pressure, okay, and this point will be point number 3. This is the sprue, and the height is like h2, this is hc, and this the total height is ht, say it is h. Okay, so this is as this cavity is open to atmosphere, so the mold is, so here the pressure will be p atmosphere. Now applying Bernoulli, if we apply Bernoulli between point 1 and 3, so if I'm applying Bernoulli equation between point 1 and 3, so I need to write it as h1 plus v1 square by 2g plus p1 by rho g. This will be equal to h3 plus v3 square by 2g plus p3 by rho g. So from here if you see like the pressure at 1 and 3 will get equated, as p1 and p1 is equal to p3, and which is equal to atmospheric pressure. And v1 will be equal to 0. So from here like you will get like v3 as root 2gh1, right? If straight sprue is used, like v2 will be equal to, so now if you will see like if you apply Bernoulli equation between point 2 and 3, if you write it as like h2 plus v2 square by 2g plus p2 by rho g will be equal to h3 plus p3 square by 2g plus p3 by rho g. So if you will apply, if it is a straight sprue, then v2 will be equal to v3, as the diameter is the same, and these will be get equated, okay, and then hc you can take it as a datum, and then it will be 0. So what you will get, what you will be left with, h2 plus p2 by rho g, this will be equal to p3 by rho g. Okay, So here, from here you can see like P2 is less than P3, which is not a favorable condition. Here at the pressure at 2 is less than pressure at 3. So what will happen? This is called the aspiration effect. So as the pressure is lower, so the gases will so there will be vacuum will be created, and the gases will try to, from the molten stream, the gases will try to go to this in your system, and then which will result into the production of the porous cavity, which we don't want. Okay, so what the general practice is made. So firstly, let me clear this. Better leave it here only. So the general practice is to let me add insert. So the general practice is to made a taper cavity. Okay, so this is what the general practice is, to use a taper cavity instead of a straight cavity. So this is the general practice to avoid this, and then this is okay. So this is the total height. So this is the total height, and then this will be the H2. Okay, so and this is this HC, and some kind of like parabolic section is generally provided here. Okay, so now again, if you will apply Bernoulli equation between point 2 so between point 2 and point 3. Point 3 is at the same location as the previous case. If you will apply the Bernoulli between these two, then you can write it as like H2 plus V2 square by 2G plus P2 by rho G. This is 2. And this will be equal to H3 plus V3 square by 2G plus P3 by rho G. This H3 will be 0 due to the, as it is at the datum, and V2 won't be equal to V3 as this is not a straight sprue. So but the P2 will be equal to P3 due to the atmospheric pressure. Now you can write it as like H2 plus V2 square by 2G. This will be equal to the V3 square by 2G. So this is what you will get. So now if suppose like the area of cross section at point 2 and point 3 are A2 and A3. Okay. So now if we will write the continuity equation, we can write it as for point V2, we can write it as V2 will be equal to E3 by E2 times V3. Suppose this term E3 by E2 is R, then R times V3. Then this H2 will be equal to the V3 square by root 2G. Yeah, V3 square by 2G into 1 minus R square. Now if we need to find the relation between H2 and H3 in terms of E3 in terms of the areas, what we can do, so from here we can see like if we write V3 here, V3 will be equal to root 2G H1, or H1 we can write it as HT. Okay, so V3 we can write it as like root 2 GHT, and from this formula if you will find the R square, so H2 will be equal to HT time 1 minus R square, and R is A3 by U2. So finally you will get like R is equal to HC by HT root. Then if you can put it like R as A3 by U2 square, so this will be the A3 by A2 square will be equal to root HC by HT. Okay, so this is like a parabolic equation. You can compare it as with y is equal to kx square. Okay, so like generics of like down screw should be parabola. This should be the parabola. Practically it is very tough to produce, and then due to its manufacturing cost and complexity or the high production cost, so the usual practice is to like slightly tapered or slightly tapered instead of a parabola. Okay, then so like we will move to this problem again from to avoid the air aspiration effect. So in a gating system design, a down screw of 180 mm in length has a diameter of 20 mm at its top, and the liquid metal in the pouring cup is maintained up to 60 mm in height. The diameter of the down screw at its lower end to avoid the aspiration effect will. Please try to solve this, as we have like already like covered what is this effect and how to prevent it. So please try this. Yes, Neelam Kumar, you want to say something? Okay, so please try to solve this problem like or Okay then, so if anyone solved this problem, anyone who got the answer. Okay. So if you will see like in a gating system, a down sprue of 180 mm. Okay, so sorry. So firstly, you need to make a diagram to understand like what it is saying. So if you see, so in a gating system, a down sprue of 180 mm. So this height is 180 mm. So this height is 180 mm. In has the diameter of this dia is 20 mm. The liquid metal in the pouring cup is maintained up to 60 mm in height. So this height has been maintained like 60 mm. And the diameter of the down sprue at its lower end. So we need to calculate this dia. This D3, suppose this is D3 or this is D2, which is given as 20 mm. So we need to calculate this dia D3 to avoid the air aspiration effect. So as we have like already derived like the relation between their heights and then their areas, so we can write it as like E3 by E2, and we can equate it as V2 by V3. R then it is equal to total height HT minus H2 divided by HT. Okay, this H2 is like the sprue height. H2 is sprue height, and then we see okay. So H2 we know that it is like 180 mm. Then this HB is HT basically will be equal to the 180 plus 60 na. Okay, so HT will be this piston height plus this sprue height. So this sprue height is like 60 mm. So we can find this HT as the sum of the 180 mm plus 60 mm. So this will be 240 mm. So now if we like calculate, E3 by E2 will be like we can write it as D3 by D2 to the square. This will be equal to V2 by V3. Okay, so this square will be equal to, this will be equal to root HT is 240 minus 180 divided by 240. Here you will get it as D3 will be 14.14. D2 is given to you like 20 mm as 20 mm. You can put these into this equation and then you can calculate the D3. Anyone who has got any doubt in this aspiration effect and this problem? Okay, Okay, then let's move to the problems of the gating ratios. As you can see, the gating ratio, which is a term which is used to classify the gating system. So generally, the gating system are pressurized, unpressurized gating system, or pressurized gating system. Both have their advantages and disadvantages depending upon the particular type of material which needs to be poured. The gating system, whether gating system is utilized as like pressurized or unpressurized, depending upon the application generally. So as you can see from diagram, the gating system is the ratio of the sprue area, which is this sprue area to the runner area, this runner to the ingate area, these ingate areas. So if you will see if you will discuss if we discuss about the unpressurized gating system, so we can say like it is a gating system whose total surface area of the doors increases gradually towards the mold cavity. It is larger than the narrower downspout. So it is saying that these areas increases gradually towards these area you can imagine as tapered coming outside. So these areas are increasing. While for the pressurized gating system, it is a gating system whose cross-sectional surface area decreases gradually towards the mold cavity, smaller than the narrowest down sprue runner area. So here the cross-sectional area gets decreased gradually towards the mold cavity. Okay, so we can write it as so generally the pressurized gating system is utilized for the iron or brass, while the unpressurized gating system is utilized for aluminum and magnesium. So if I will write it as so for example, if I write as the gating ratio as 1 is to 0.75 is 2.5. Can anyone tell me whether it is a pressurized gating system or a non-pressurized unpressurized gating system? So if you see as the gating ratio, it is ratio of sprue area to runner area to gate areas. The area is consecutively decreasing, right? And from the definition, you can see like will be a pressurized gating system. So the area decreases gradually. Okay. Or some other examples, I can write it as like 1 is to 2 is to 1. This is also example of pressurized gating system. Okay, or 2 is to 1 is to 1. And this is a pressurized, or suppose if I write as it is like 1 is to 2 is to 2. This will be an example of unpressurized gating system, or 1 is to 3 is to 3. Both of these are examples of unpressurized gating system. Okay, so let's move to the problem number 6. It says like for a bottom gating system, the height of the down sprue is 180 mm. And the circular ingate diameter is 25 mm. The cross-sectional area of the sprue for a given gating ratio 1 is to 2 is to 2 in centimeter square will be. So firstly you need to see like what is this gating ratio is. So gating ratio is, you need to write it as, so you will write it as gating ratio. It is a ratio of 3 areas, and these areas are sprue, then runner, then comes the gating. Okay, so for a bottom gating system, the height of the down sprue is 180 mm and the circular ingate diameter is the cross-sectional area of the sprue for a given gating ratio will be. Okay, so this is the gating ratio which is given as 1:2:2, and then the height of the down sprue is 180 mm. Then the diameter of the gates is given as 25 mm. So gate area you can directly calculate as pi by 4 d square. So once you found the gate area, you can find the others area easily, right? This is the problem. This is the simplest problem, I think. So if you find like area of the gate, it will be pi by 4 into d square. It will be 25 square. So from calculating it, you will get it as like 4.91 centimeter square. It's area of the gate. Then you, from the question, you need to calculate the cross-section area of the sprue. So this sprue area will be, so area of the sprue divided by area of the gate, area of the sprue divided by this area of the gate. From the given question, it is 1/2. So you can directly halve this area, and then you can see like area of the sprue will be half multiplying by this 4.91. So you will get it as like 2.45 around centimeter square as your area of the sprue. So this is your answer. Okay. So next, so if anyone has any doubt in this question, we can discuss, or let's move to another. Okay then. So if you move to the problem number 7, it says like for a gating system of some alloys, there are 3 ingates. Okay. Okay. So there are 3 ingates, and the cross-sectional area of each ingate is half of the area at the bottom of the sprue. The runner has a cross-sectional area equal to the twice the area of the gate. The gating ratio of the system will be. These are the options. Can anyone like tell me like what will be the answer? So like if I don't know why not like there's no discussion today. Okay, then if we see like so in the question it is given like the area of the runner has a cross section area equal to the twice the gate. Okay, and okay, so area of the gate is so area of the gate is half that of the area of the sprue, and then area of the runner is twice the area of the gate. And we can write the gating ratio as area of the sprue to the area of the runner to the area of the gate. If you see, if you will write, if you convert it to the all to the one term, then area of the riser we can write as twice to the area of the gating. Then this will be again area of the gate is half the area of S. From here again we can convert this area of the gate to half of the area of the sprue. So this will be like area of the sprue times this will again it will become area of the sprue times area of the sprue by 2. So from here we will get it as like 1 is to 1 is to 1 by 2, right? And then this will be like converted to can be converted into 2 is to 2 is to 1. So majority of the people or some of the people like uh, will write it like will found that 2 is to 2 is to 1 is the answer. But what we need to like carefully see for a gating system there are 3 in gates. Okay, so whenever this problem comes you need to read carefully. So there are like 3 in gates. So if if it was in the answer due to the like to solve hurriedly, like people might have like take 2 is to 2 is to 1. This is the wrong answer. So whenever this like the problem comes there are 3 ingots is given, so directly you need to multiply it by 3 times. And the correct answer will be 2 is to 2 is to 3. So you need to consider all the gate. Okay, so F will be the right answer. So let's move to the next problem. So this is like again a simple problem, so I would like to you to please like see whether it can be solved. So an aluminum casting having a gating system with a gating ratio of gating again this gating ratio is given as like area of the sprue to the area of the runner, the area of the gate it is given as 1 is to 2 is to 2. Okay, for a discharge which is given as q is equal to 100 cubic centimeter per second, if the maximum velocity in the gating systems if the maximum velocity in the gating system should be 10 centimeter per second, the area of the gate. So velocity in the like gating system it is given as like 10 centimeter per second, and we need to calculate the area of the gate ag in centimeter square. So can anyone like solve it? This is a simple problem I think. Okay then, so if you see like you can directly write the q as, you need to equate it like a time velocity. Velocity is given as 10 centimeter per second. From here we can find like this area is 10 centimeters square. Then from this gating ratio we need to like as we need to find the area of the gating, this will be like equal to twice time 10, which will we will get as 20 centimeters square. This will be your answer. So till now, anyone who has any problem in any of these problems which we have discussed today, like he or she can tell like if in any problem you faced or want to discuss again. Okay then, so let's discuss few things like which we will be discussing in the next week. So in the next week, like we will be discussing the problems of the riser designing. I will briefly discuss them. Like these are already been covered in the theory, but still. So we will discuss about the problems of the riser design. So there are methods which have already been covered by the Professor Jha in the theory. So these are like one method is the shrinkage volume method. Second method is like the Keynes method. Then the third is the modified Keynes method or Naval's method. Then the final one is the modulus method. Okay, so like we will discuss the numericals of these problem in the next class. Firstly, like if you discuss about the shrinkage volume method. So in short form I will write is like SVM. So shrinkage volume method. Okay. So if we discuss about the shrinkage volume method, so suppose the volume of the riser is like so as per this method, the volume of the riser should be greater than or equal to like 3 times the percentage of shrinkage of the volume in the casting. Okay. So you can write it as volume of the riser should be greater than or equal to 3 times the percentage of shrinkage volume of the casting. And then from here, and another thing is the solidification time of the riser. It should be greater than or equal to desolidification time of the casting. So the riser should be solidified after the casting. Then only it can give the melt. The melt can flow from this to the from riser to the cast. So this we can write it as desolidification of the riser as V by A time of the riser should be greater than or equal to V by A of the casting. Okay. So this is the first method whose numericals in detail we will be discussing in the next class, and then you can go through the theory of the Professor Char's lecture for a detailed theoretical thing. I'm just discussing in briefly for the numerical purpose of thing. Then if you see the second method, which is the Keynes method. So according to this, he defined a term called the freezing ratio. In short, FR. He defined it as the ratio of the V by A of the riser to the V by A of the casting. And there are he then defined two things volume of the riser to the volume of the casting as Y and X as A by Y minus B plus C. So what you need to do, you need to calculate these two terms X and Y, and then there is a graph he gave which is the between VR by VC and this freezing ratio. So if it is below this, then your casting is defective, while above this it will be the sound casting is sound casting. Okay, so you need to plot the curve between these two terms and calculate it from here, and then you need to put C from this graph to you can find out the values. The more detailed discussion and detailed problem we will do in the next class. Now then, if you see the third method, which is a Naval's research method, let's write it in short form as NRM method. So he defined a term called shape factor, which is the ratio of the length plus width divided by the thickness of that particular. So if you calculate the shape factor for a cube, can anyone tell me what will be the shape factor for a cube? So for the cube, all the sides are same, so L plus W will be 2 times thickness, or it will come as 2. Similarly for the sphere, it will come as 2. And for cylinder also, with h equal to diameter, it will come as 2. Okay. And so he gave this curve between shape factor and volume of the riser to the volume of the casting. And here also you get the defective and then the sound. Okay, so next if we will see finally the modulus method. So modulus is the ratio of the volume of the particular casting to the area of the casting, or for the riser it is the ratio of the volume of the riser to the area of the riser. And if in question it is not given what is the relation between modulus of the riser and modulus of the casting, we generally take it as 1.2 times modulus of the casting. Okay, so now if we see so these are the four methods whose problems we will be discussing in a detailed manner in the next class. Okay, and then one more thing is which we need to discuss is the some things some small things like casting yield. Sometimes it may come as what is the casting yield. So casting yield. So if you see casting yield, it is the so your gating design it should be proper to avoid erosion, turbulence, and splashing, and air aspiration also, so that non-ferrous metals can also be easily casted. It tells how easily your casting can be casted basically. So casting yield, it is the ratio of the volume of the casting divided by the volume of the casting and plus volume of the gating. Sometimes in exam it comes and we don't know the terminology. So casting yield is the ratio of the volume of the casting to the volume of the casting plus the gating system. Okay, and then if we see one more thing, ideal shape of the sprue is parabola. Ideal shape. But due to difficulty in manufacture, it is made tapered. And if you talk about the runner, so trapezoidal for the runner, it should have minimum frictional head loss. So trapezoidal cross section is having minimum frictional head loss, but circular cross section is best for minimum heat transfer. So it is preferred. Okay. So generally, I have discussed, I think majority of the things. In the next class, we will be doing these problems on Keynes method and other three methods. So what should we do? Okay. So let's do a simple thing as we have time. So suppose there is a dimension of a cylindrical side riser used for casting brass cube of 20 centimeter dimension if the volume shrinkage is 9%. If this is given in your question, so how will you calculate the dimension of a side riser? So I will write it for you. And the question is the dimension of cylindrical side riser which we need to calculate used for casting brass cube of 20 centimeter dimension if the volume shrinkage is 9%. So this we need to see how to solve this. So for any type of riser, so first we, as it is in theory, it is already been covered. Generally If nothing is mentioned in the question, for the side riser we take it as H is equal to D. Okay. So for side riser, I'm taking as H is equal to D, and then the volume of the riser is 3 times 9%. It is given as volumetric shrinkage to the 20 cube of 20, because it is a cube, brass cube it is. Okay, so the volume of the riser is pi r square h. We will equate these two. Okay, from here we will get r as h barabar d. So from here we will get r as 7 centimeter. This is the first step you need to do. This is your step 1. Now coming to the step 2. So now V by A of the riser is D by 6. Okay, if you will calculate it, it will come as 2.33. Okay, now from here we can calculate V by A of the casting as 20 cube of 20 divided by area will be the 6 times side square. So it will be like 3.33. So from these two equations we can see like V by A of the casting is more than V by A of the riser. So we can conclude that the riser will solidifying before, as it is lesser than the value is lesser than the V by A of the casting. This shouldn't be the case. Okay, then so what we need to do? Now comes the step 3. We need to ensure that our V by A of the riser is greater than or at least equal to the V by A of our casting. So from here you can see, like, if we write it as this should be greater than or equal to 3.3. So our R comes of the riser should be at least greater than or equal to 10 times 10, and our H should be greater than or equal to 20. Okay, so this is the basic problem, like how to approach it, how the our approach should. So firstly we calculated the from the given things, like what are the radius and height of the riser are, and from those we calculated it. We calculated or equated it to see like what are the to whether the conditions of V by A of the riser and V by A of the casting are being met. So we found like these are not meeting. So we need to ensure this should be that, like, we need to ensure that our riser should solidify after the casting. So we put it, we ensured it in our step 3, and then we found the H and R of our like H and R from our like step 3. So this is the general thing. So we will discuss more problems. There are many problems on this topic, and I'll ensure like majority of the problems are being covered. Okay, in the next. Okay, so If anyone has any doubts on the today's problems, or he or she wants to like discuss more of about any particular problem or anything, we can discuss now. So in short, today we discussed about the uh, firstly we discussed about how to solve in week 3 and week 4 combinedly, like we wrapped up the filling problems of the simple getting, top getting, bottom getting, and parting line getting system. So the basic idea how to solve these problems you have now. And after that, we also discussed like how the derivation revisited them. Like you can again go to the lectures or the theory of the Professor Jha for consolidating your basics. And after that, like
All right.
and after that, we solved and after solving the top getting, bottom getting, and parting getting system problems. We discussed about the aspiration effect in detail. And then we calculated the relationship between their height and the areas and why this should be tapered. And after that, we discussed some problems of the gating ratios. And finally, after solving this problem, we discussed whether what we will be discussing in the next week. So in the next week, like we will be doing an extensive numericals on the riser designs from these four methods, which have already been covered in the theoretical part by the Professor Jha. So and then finally like I like solved a simple problem to give you a basic glimpse what we will be discussing more in the next week. So besides this, if anyone has any doubt, we can discuss now or we will close this session. Thank you, Ajinkya. Okay, then we will wrap up this today's fourth week session of the tutorial and hope to see you in the next week. Thank you for being present here. Okay, then I'm closing the session. Thank you.